question asks about which of the two types of errors is more important. I remember on Wednesday, actually talk about type 1 and type 2 error. And you can see today's topic, we want to focus on how we compute type 2 error. But I first want to say this. If you want to answer a question, which of the two type of error is more important, then I'm actually going to say the significance, okay, of any type of the error here depends on the context. Okay, so I'm going to give you 4 scenarios, and we can actually judge ourselves to be able to see which of these types of error is more important. Okay, I'm going to start from medical field. Okay, in a medical field, okay, type 1 error can be committed, okay, in a situation whereby maybe we are introducing a new drug and we took a decision that the new drug is actually going to add a medical benefit to the patient, and nature knows the truth, right? Maybe by nature the drug does not have any effect. Okay, in that kind of situation, type 1 error is committed, and of course, that will lead to waste of resources. Okay, because we're actually going to have what I call unnecessary treatment and unnecessary medical intervention. That is the type 1 error. Okay, but on the other hand, still on medical field, when we talk about type 2 error now, type 2 error is committed, okay, when maybe by nature that particular drug is supposed to do a great job, like it's supposed to add a significant I mean, in terms of effect, okay, it should be significant, but we reject that notion, okay, so which means we miss an opportunity to add into medical value of our patient, okay, and that is actually going to lead to what I call delay in treatment, and that could be harmful to the patient. Okay, so we can actually compare. Okay, the two are dangerous, whether type 1 or type 2. Now, before moving forward, I'm actually going to mention the effects in industry. In industry, no matter how we try, we're always going to have defective, right? Okay, now imagine situation whereby we actually reject good lots, okay, good products, okay, rejecting good products. What do you think is going to happen? Okay, the product that's supposed to be good is rejected. Okay, that is going to be waste of resources, because you use resources to make the product and you reject it when you are not supposed to reject that. Okay, now the type 2 error, on the other hand, is actually going to be your failure to identify a defective, a bad product. Imagine pushing a bad product to the market that could lead to safety issues, and in fact, customer dissatisfaction. Okay, now I'm going to say the last thing in national security that is very vital. In national security, imagine what was perceived to be a threat. If what was perceived to be a threat, okay, is not even in existence, what do you think will happen? That's a false positive alarm. Okay, imagine what is going to happen. You start deploying resources, and not only that, there is going to be an infringement on civil liberties. Not only that, there will be tension. You create tensions here and there, and there's also going to be what I call a strained international relation. Okay, now let's talk about the type 2 error now. The type 2 error is when you miss a genuine threat. Imagine that. What do you think the consequence of missing a genuine threat on national security is actually going to be? It could be terrorist attack, it could be espionage, or before you know the national security, or if our national sovereignty will be in danger. Okay. And what do you now think we need to do in manufacturing industry to control for type 1 and type 2? That is why they have quality control office. They have to do their job. In national security, okay, how are they going to strike a balance between a type 1 and type 2 error? And that can actually be done through national security effort of surveillance, risk assessment, having a diplomatic engagement with other nations, and so on like that. Okay, now the two types of errors are very, very important. Okay, but let me tell you this. If we want to conduct a statistical test, we normally start by specifying the probability of type 1 error, which I call the level of significance, but the probability of type 2 error, if I can figure out the probability of type 2 error, then I will be able to figure out the power of a test. The power of a test is ability to take correct decision. So the moment I feel I'm able to figure out the probability of type 2 error, then the type 2 error and the ability to take a correct decisions are mutually exclusive. Now I think I've just justified reason behind what we want to do. Then I want to take into mathematics aspects. Okay, now right now we actually want to test. We're testing hypothesis. Okay, you see that hypothesis testing. That's an upper tier test. You can see the alternative. Okay, and you know, uh, under a sufficient large sample size, we expect the theta cap. Don't forget, if I want to test hypothesis about the values of a parameter, we're normally going to focus on estimator, theta cap. And that was the reason why the other time we were trying to investigate how good is our estimator. Don't forget, we actually want to use estimator to represent the unknown value of the parameter. And of course, so the variance of the estimator actually exists. And depending on which estimator you are talking about, you may be talking about maybe the proportion, or you're talking about the estimator for mean. The estimator for proportion is actually the p-cap, and we believe that under a sufficiently large sample size, the p-cap will follow normal distribution with the mean of that and the variance of that. And as you can see, the p-cap depends on the parameter p. Okay, but when you make use of the y-bar, okay, which is another estimator for the mean, that does not depends on mu. I just wanted to take note of that. Now, when the central limit theorem applies the idea of a standardization, the standard z-score can actually be used. And if that happens, you remember the other time I walk you through the rejection region. Okay, the rejection region can actually be figured out if I add the hypothesized value of a parameter plus the margin of the error. The margin of the error is a product of the Z quantifier. Okay, the Z quantifier now giving any level of significance alpha that we call the probability of type 1 error. You can see in figuring out Z-score, we put into consideration the probability, the maximum probability of committing type 1 error, which is alpha, and multiply by the standard deviation. Okay, and at the end of the day, we said that the type 1 error rate alpha, you can see that we've already considered type 1 error rate in our finding. Now, suppose alternative is true. Okay, if alternative is true, it means theta is not going to be equal to theta naught. The theta will be greater than theta naught, and greater than theta naught, maybe we're talking about theta A. Okay, theta A. The values of the parameter assumed by the alternative. Okay, so suppose HA alternative is true, which means that very drug that you are testing the new drug by nature is supposed to be significant, but you reject that. Okay, when you reject that, of course, you know type 1 error rate is actually made. Okay, now if you take a look at this guy now, what am I doing? What I'm actually doing here, oh my God, I'm actually putting into consideration a z-score that has to do with not when the null hypothesis is true, and a z-score when the alternative hypothesis is true. Take a look at it too. I got two different values of z-score here. Okay, one, when the alternative is true. When the alternative is true, it's just going to be estimator minus the value under the alternative divided by the standard deviation of theta car when the alternative is true. But take a look at the Z0, that actually centered on when the null hypothesis is true. Okay, I needed to pay attention now. We want to figure out the probability of type 2 error. Is very, very important. You know, the probability of type 2 error is something that's supposed to be significant, but we reject that. Okay, so we want to figure that out. Okay, and if I want to figure, I told you the other time, the symbolic representation of type 2 error is beta. Y for the probability of type 2 error is beta. Y alpha is a symbolic representation of the probability of type 1 error. So what do we mean by the probability of type 2 error? Is the probability that we fail to reject H naught when alternative is true. Okay, because when alternative is true and we don't accept alternative, okay, we fail to reject the null hypothesis, that's an error. Okay, now that is what we mean. Okay, now if you take a look at what I have right now, okay, why do I have an estimator less down? I got an estimator less down because the nature of the test is actually greater than, and you know if it is greater than, the rejection region is going to be greater than. Okay, but if I want to talk about the probability of type 2 error, I'm actually going to go against the rejection region, which is going to be the complement of greater than. That was why you see this to be less than. Does that make sense? Okay, any question on this? Okay, now if I have that and I actually trying to simplify, okay, I'm actually you're gonna see that we're gonna get this guy and simplifying further. Okay, we actually gonna have this guy where we can then finally we actually so what are you seeing now? Okay, so what are we actually seeing now? Okay, so what we're seeing now, if you take a look at this guy, how do I go from here, okay, to here? What have I done? I'm actually, you see that I'm subtracting from the theta naught. I subtracted theta A, okay? You see that? And I subtracted theta A from the estimator too. I subtracted theta A from both sides of the IO, and when you can see that exactly, and I divided by the standard deviation. Is there anyone who doesn't understand how I go from the second line to the third line? Is there anyone? Please, I need you to pay attention. I know this is mathematical. Okay, in case you need clarification, I need you to tell me now, how do we move from the second line to the third line? We subtracted theta A from the both side of the IO. Okay, and after doing that, that was why you see a theta A here being subtracted from that, and theta A being subtracted from that, and we divided both sides by the standard deviation. Take a look at that, and when we do that, this will automatically qualify to be a z-score. And what kind of z-score is that? That will be z-score for when the alternative is true. Why? Is it because it's centered on the mean of the estimator here is actually assumed to be the values of the alternative. and the standard deviation here is actually assumed to be, the standard deviation of the estimator when the alternative is true. Take a look at that. Okay, now this guy now is a z-score that has to do with the alternative. Okay, and z-score is normally distributed with a mean of 0 and a variance of 1. Okay, so what I have here is still what I have here. What am I doing? I'm trying to set up, if I want to find the probability of type 2 error, this is going to be the formula. That's what I mean. Okay, now I want to walk you through an example now. Please pay attention. Okay, now suppose that the vice president in example 10.5, we did an example on Wednesday, okay, where a vice president make a claim. Okay, we want to be able to dictate a difference equal to 1 call in the mean of customer call per week. That is, it wishes to test, okay, this vice president want to test this, that mu equal to 15, okay, and mu equal to 16. If I want to rewrite the alternative, you know what I'm going to write in terms of 15 is the same thing as mu greater than 15. Does that make sense? The alternative here, because it said mu equal to 16, so this is the same. If I want to write it in terms of the non-hypothesis, so this is going to be like mu greater than 15. Okay, because that is telling me that the direction of the test is actually going to be upper tail. What if mu equal to 14? That would be less than. Does that make sense? Okay, and the direction of the test will be specified by the alternative. Does that make sense? Now, I want to, the estimator under investigation is Y bar. Then my rejection region we have a greater than sign. Why do I have a greater than sign? Because of what you have in the alternative. Does that make sense? You see the way the rejection region is set up. Okay, we don't just put a sign here. We don't just put greater than or less than. What we're actually going to put depends on the nature of the alternative. Now, if you take a look at if you sketch a normal curve for the two hypotheses, the one in blue is the one, what is the center of the one in blue? 15. What is the center of the other one? 16. Take a look at that, because we are actually testing between two hypotheses, mu equal to 15 and mu equal to 16. And of course, you can see the shaded parts, we can indicate the type 1 error rate and the type 2 error rate. So take a look at all of that. And if you pay attention to what come at the point of intersection of the shaded line, that is actually going to be the mu naught plus the sigma alpha. If you take a look at sigma, sigma over root n, that is the standard deviation of the mean. Don't forget Y bar is the random variable, is the estimator here. Okay, and of course we're going to have that. Now, if I now want to compute my probability of type 2 error now, okay, take a look at that. The probability of type 2 error now is to fail to reject the non-hypothesis when the alternative is actually true. Okay, now if you take a look at what we have right now, okay, if you want to find the type 2 error, what are you going to do? You're going to go against rejection region. Alternative hypothesis the other time was mu greater than 15, and the rejection region was greater than. Whenever I want to compute the probability of type 2 error, you should use the complement of the rejection region. Okay, that was why you see a less than. Okay, now when you take a look at this guy, now take a look at that. Y bar less than that particular guy that we talk about. Take a look at that. Okay, any question about that? Any question? Do you know what we're going to do now? will be similar to what we did the other time here, where we were subtracting theta A. You remember, moving from here to here. What do? We subtracted the alternative from both sides of the IO. We divided by the standard deviation. That is exactly what we want to do here. Okay, take a look at that. That's what we're doing here. What are we doing now? What are we doing now? We're subtracting from both sides mu A and divided by the standard deviation of the estimator. What is the standard deviation of y bar? It's sigma over root n. Okay, do you see that? Do you catch that? Take a look at that. That is how we arrive at this. Oh, give me 1 second. Why is this writing this way? Okay, let me take it cool. Okay, take a look at that. Is there anyone who doesn't understand how we got here? We subtracted both sides from both sides, the mean in the alternative, divided by the standard deviation of the estimator. The estimator here is y bar. Oh my God, that's going to give me an opportunity to be able to say this guy is a z-score. Okay, this is another way to write a z-score. A z-score follow a normal distribution with a mean 0, 1, mean zero variance 1. Okay, and when you take a look at what I have here now, okay, if this guy here, give me 1 second, this guy divided by this guy, which is what you have here, and this guy divided by that, the sigma over root n we cancel out. Any question about how we get to this junction? Is there any question? Go ahead. Okay, what do I mean by finding the complement if the rejection region is greater than? Whenever I want to find type 2 error, then I will go against greater than. What is the opposite of greater than? Less than. That's what I mean. And if the rejection region is less than, if I want to compute type 2 error, then I'm going to use greater than sign. Does that make sense? Okay, now this is what we have now. If I want to figure out type 2 error, okay, and I'm working with the mean, okay, this is what I'm going to that's what I'm going to use. Okay, now let us now solve. Let's take an example. Let's say, in the example that we are working on, we're given that the value under the null hypothesis is 15, and the one under the alternative is 16. Okay, now I'm using this formula that I derive here. I want to use this particular formula here. Or what I'm just going to do, oh my God, I can make use of a z table, provided if I know this guy, standard deviation, the sample size, I can check this from the table. I should be done. That's exactly what I'm doing here. Is there any question? What I'm doing here, I've already plugged in, okay, the mu naught, the mu A, the sample size, the variance, okay, and I've checked from the table. You can see 1.645, right? Well, I think the alpha was maybe 0.05. We check for Z alpha, and we arrive at this guy now. Okay, finally, when you simplify that, you're actually going to get this guy. What are you going to do here? You actually trying to say you want to check from the table, okay, the probability of Z less than negative is 0.335 or 355 rather. Okay, so and when you do that, okay, you're actually going to get the result, multiply that by 100. That is what you have, which is the probability of type 2 error. Is there any question? This is the probability of type 2 error, 36%. Go ahead. Exactly. Yeah, the alpha will be according to the significance level of the test. Yeah, that's correct. So which means if I want to find type 2 error, I've already decided on type 1 error. we're always going to assume that type 1 error. Before you find type 2 error, they are connected. Okay. Now, this is fairly large. That 36% is fairly large. Okay. Now, how to control type 1, type 2 error rate? The other time when I was walking you through this, when we made an attempt, to improve on type 1 error rate, the type 2 error rate is going to go up because they are inversely related. I remember we tried changing rejection region. When you extend rejection region, then you are shrinking acceptance region. But you know what? Can we have a way to simultaneously, control the type 1 and type 2 error? Just like what I was telling you the other time. Okay. When I was giving an example on national security, then we're going to increase our sample size if we want to have both controlled. Does that make sense? Okay. Okay. Now, and I want you to see it, which means, I've already said this. We need to increase our sample size. If we need to increase our sample size to what? And that is the reason why we need a sample size determination. Does that make sense? Statistics is like a story that goes on and on and on. They are connected. Why do we find ourselves here now? Why we find ourselves here is the way to control both type 1 and type 2 error is actually to increase the sample size. Now, increasing the sample size to what magnitude? How small? What is the least sample size we can actually have to be able to minimize both type 1 and type 2 error rate? Now, I want to go back. It now depends on what you are looking at. Let's say we're focusing on testing the mean. Okay. We actually want to figure out the true values of the mean, and we're focusing on an upper T test where the alternative is greater than. Okay. Of course, where the alternative is greater than the estimator will be a sample mean, right? We're going to follow a normal distribution with that and that. Then the corresponding rejection region is actually going to be y bar greater or equal to k. Okay, greater than or equal to, because of the fact that the alternative is an upper T. Now, I need to pay attention now. If I actually want to decide on controlling both type 1 and type 2, okay, and I want to figure out the sample size, I think I need to follow first, like, with type 1 error rate, what sample size do I need? With type 2 error rate, what sample size do I need? With a combination of the two, what sample size do I need? Take a look at this. I want to find the type 1 error rate, the probability of type 1 error. Now, the probability of type 1 error is going to be y bar greater. Don't forget, if I want to find probability of type 1 error rate, I'm actually going to use a sign from the rejection region. But if I want to do the probability of type 2 error rate, I'm going to go against that. Does that make sense? Okay, now, which is going to be greater or equal to k, given that mu equal to mu naught? Mu naught is what you specify in the null hypothesis. Now, what are you going to do? The next thing you're going to do is to subtract. If you take a look at what I have now, we are actually subtracting mu naught, because why are we subtracting mu naught? We're focusing on type 1 error rate. We're subtracting mu naught from that divided by the standard deviation of the y bar. That's exactly what we're doing at both sides. Okay, that's what we're doing at both sides. And finally, this guy is a z-score now. Okay, we're actually going to say the probability of a z-score greater or equal to that. Okay, now what do you see? The probability of type 1 error rate depend on the sample size. Does that make sense? Okay, if that depends on the sample size, can we also approach that of the type 2 error rate the same way? Of course, if I want to do type 2 error rate, oh my God, what has happened now? I've changed the greater than to less than because I'm focusing on type 2 error rate. Okay, then what am I going to do? I'm going to subtract the mu A, which is, the mu under the alternative from both sides, then divided by the standard deviation. That's exactly what I'm doing here. And at the end of the day, Okay, take a look at what I have. Do you see that? That's what I have. I've been able to derive that, which is also a function of the sample size. If that happened, do you know, I can bring the idea of a system of equation in where I'm going to have both, look at the two now, okay? The probability of that greater or equal to that equal to alpha, and the probability of this less than that equal to beta, okay? Now, do you know I will be able to control for type 1 and type 2 if I want to solve this guy simultaneously to be able to know the sample size, then I need to specify the type 1 error and the type 2 error that I want. Does that make sense? If I specify the type 1 error, if I specify my alpha, if I specify my beta, okay, that I want as maybe as lowest as possible, then I will be able to determine, I'll be able to get the sample size that I need, okay, the sample size that we actually attain that my specification. Now, if you take a look at what I have right now, if I want to solve for this guy, okay, this is going to be equal to Z alpha. That's why you have this equal to Z alpha, and the other one here is going to be equal to negative Z beta. Okay, just take note of that. Okay, what am I gonna do? Oh my God, I'm actually gonna solve for K. Okay, you know, solving for K here. Solving for K here will actually give me this. And solving for K in the other one, it will give me that. I solve for K here. It's give me this. I solve for K here. K equal to K. Then I equate the expression. Equating the expression. Now I will be able to solve for N. Okay, finally, what are you gonna see? Oh my God, this is what you are seeing finally. If I want to, this formula can actually be used to figure out the sample size. If I fall first, I need to specify the type 1 error rate and the type 2 error rate that I need. Does that make sense? That is what we do in research. To be able to figure out the sample size. We don't just go into feed. We don't just go into population to just select whatever sample size. We put into consideration type 1 and type 2 error, the probability of them. Okay, can you see now? Okay, now if that is taken, so this is the formula that we just derived. We should call this samples, but this very formula is for what? When we are focusing on upper T test. Don't forget, the alternative hypothesis was a greater than sign. If the alternative is not greater than sign, it's not going to be this. It's going to be something else. Does that make sense? Okay. Now, I need you to take a look at this. I want us to talk on this briefly. Do you know sample size depend on the variance? When variance goes up, samples, you know, that depends on that. And samples, and that was why we said N is an increasing function of sigma squared. And it's a decreasing function of the difference between the alternative, what you specified in the alternative, and what you specify in the norm, because that is occupying the denominator position. Okay, take a look at that. Okay, so N is a decreasing function of alpha beta. Okay, remark, minimum sample size for a lower test is the same. Okay, so you're still going to have that when you can, but I needed to try and derive that and see for yourself. But if I want to do two-tail, let's say for instance, my hypothesis is two-tail, alternative hypothesis is not equal, we are not going to have a closed form solution. Okay, maybe we can seek redress using numerical approach. Okay, I just wanted to know that. Now, can we put this formula to test? Let's get started. We want to put this formula to test. What are we doing? We want to figure out the sample size given type 1 and type 2 error. Okay. Now, suppose that the vice president in the example that we done before, mu equal to 15, mu for non-hypothesis, then equal to 16 for alternative, and we set our type 1 error rate and type 2 error rate to be 0.05. We set it, okay, to be that. Then we want to figure out the sample size that will ensure that accuracy. So what are we going to do? We're using the formula now, then we're going to plug it in. Okay, that's what we're doing. And that is going to give us a sample size of 98, at least 98. Does that make sense? To be able to have that. Now, let us now look at what of in a situation where I actually did not increase the type 1 error rate, and I increased the type 2 error. When the type 1 error rate is still 0.05, but I increase type 2 error, what would be the implication? If every other thing stayed the same, what would be the implication on the sample size? Then the sample size needed will decrease to 78 from 98. But what of in a situation whereby we retain other information, but we change the value under the alternative to 15.5 instead of 16? Okay, what would be the implication? Oh my God, you need a lot of sample size, changing what you are testing. And what of in a situation, let's look at the effect of variance. Okay, so instead of you to be using 3 squared, okay, and you are using 6 squared, okay, the effect of variance, you can see that as well. So we're just trying to let you realize that. What have we just done now? We've been able to see how we can control both type 1 and type 2 error, but we can only control them, okay. The way to control them is to set a value for them and figure out what the sample size is going to be. Don't forget, the more we increase the sample size, then the lower will be the both type 1 and type 2 error. Okay, now you know what I want us to do now in the next 10 minutes. What is the relationship between hypothesis procedure and confidence interval? Okay, before I've walked you through hypothesis testing. We've done hypothesis testing. We've done large sample interval. Do they have any connection? And I'm actually going to say, yes, they have connection. Okay, now let's start. The whole thing is going to start with trying to figure out unknown values of a parameter. Okay, and if we want to figure out the values of a parameter, we need to have an estimator we're going to work with, because we actually want to take a sample. When sample is involved, parameter estimation is involved. And according to central limit theorem, okay, when you have a sufficient large sample, we expect the estimator to follow normal distribution. When the estimator followed normal distribution, we can use the idea of large sample confidence interval that I showed you before. Okay, we take a look at this guy here. So if you take a look at this guy here, of course, we have done that before. That's a large sample size confidence interval. But do you know from that, we can go to hypothesis testing? How are we going to go to hypothesis testing? From there, this guy is also the same thing as this guy, right? So what am I going to do? If I want to figure out, I can simplify this. And when I simplify this, I'm going to arrive at this. Take a look at that. I'm actually going to arrive at theta cap minus theta. You saw the theta in the middle. Okay, I'm actually going to arrive at that. And you remember the other time, the very first one that we did is actually a two-sided confidence interval. You remember in this class, we have a two-sided confidence interval. If we have a two-sided confidence interval, we're also going to have two-sided hypothesis testing. Then if you take a look at the second one, if you take a look at this guy, you remember we consider upper confidence interval and the lower confidence interval before. This is from what we've done before. Okay, now what I'm just trying to tell you, when you have a two-sided confidence interval, we're also going to have a two-sided hypothesis testing. When you have an upper take confidence, I also have upper take hypothesis testing. The lower confidence, we also have the lower of that. That's exactly. Now, what I'm trying to show you now is just to remind you of what we've done before on the last sample, but I want to show you the hypothesis version. Now, the hypothesis version, do you know that if I want to derive two-sided hypothesis, it's actually going to come from two-sided confidence interval. Is that not two-sided? Okay, it's actually going to come from there. And let me now tell you the way decision is taken. You know, in statistical analysis, if I'm testing this hypothesis, okay, we look at the rejection region, right? If the test statistic falls in the rejection region, we reject the non-hypothesis. That is the way we take our decision. But how do we take that decision using the confidence interval? Take a look at this. Okay. Now, if theta naught 4, what is your theta naught? The theta naught, the hypothesized value under the non-hypothesis, when it falls out of the two-sided. Okay. Now, when it fall out of the two-sided, take a look at this. Inside here is the acceptance, right? You are not going to reject inside here. But outside, what happened? You are rejecting, which means if you compute a confidence interval, two-sided, and you want to answer hypothesis testing of two-sided, then you reject your non-hypothesis when the hypothesized value fall outside the confidence interval. Does that make sense? Like if falls, it is smaller than lower, it's either it is smaller than lower bound or it is greater than the upper bound, that is a rejection. Does that make sense? I'm trying to tell you the way we can use the idea of a confidence interval to take a decision regarding hypothesis testing. So there's a connection between them. Okay, so, and which means fail to reject, okay, H naught, if this happen, is the same thing as if I want to use a confidence interval, if theta naught fall inside, falling inside is failing to reject. Failing to reject means acceptance. Does that make sense? Okay, now I've talked about two-sided. What about talking about one-sided? Take a look at this. What am I doing here? That's an upper test. Okay, in an upper test, I will use one-sided confidence interval. If I want to use one-sided confidence interval, take a look at the one-sided right now. For the upper T test, the corresponding confidence interval is actually going to be the one that go from here to infinity. The one that go from lower bound to infinity. You remember we did that before. From lower bound to infinity, okay, that is actually corresponding to an upper T test. Now, how do we reject? We're going to focus on theta naught again. What is the theta naught? The hypothesized value of the non, specified in the non-hypothesis when it fall inside the one-sided. Okay, when it fall inside the one-sided, okay, that is exactly what we're trying to say. Okay, now there's a lot of reason. Take a look at, there's so many things we can do. Look at this one as well. Give me 1 second. Do you see that? It's either we use that or we use this. There are 3 conditions to reject. It's either the z-score less than the z alpha, okay, to fail to reject. Okay, don't forget, what are you doing? You are testing greater than. So failing to reject will be less than. Okay, now fail to reject H naught if that happen, or if theta naught greater than that, or if theta naught fall inside one-sided. If theta naught fall inside one-sided, then you're going to fail to reject for the upper test. But what if you are dealing with the lower one? Take a look at the lower test. Okay, do you see that? The lower test, do we have a less than? okay, reject if this is less or equal to that of theta naught is greater than that, okay, then theta naught fall out of the one-sided. Okay, so what are we trying to say? We're trying to, give a kind of a comparison between the way we can actually take decision using hypothesis testing and the confidence interval. Now I quickly going to run into an example here. Okay, we have this data set. We work on this data set before. Okay, and you've been given the level of significance. We want to see the reaction time. Okay, let us take a look at this by, we do this before using hypothesis testing. But what if I want to use a confidence interval? Using a confidence interval, I'm actually going to do this. Now, take a look at this. When a confidence interval includes 0, if you're talking about difference, okay, and a confidence interval includes 0, then it means you're going to fail to reject the null hypothesis, because the null hypothesis is going to say there is no significant difference. Okay, but situation where you are from positive to positive or negative to negative, what is happening here? Negative to negative. Negative to negative means a 0 does not falls in the interval, then you are rejecting the non-hypothesis. You remember on Wednesday, we look at the reaction time. How men and female react to stimulus, right? Using the knowledge of hypothesis testing, we rejected the non-hypothesis. Right now, we're using confidence interval because of the fact that 0 is not in the interval, then the non-hypothesis should be rejected. Is there any question before I go today? It's another Friday, right? There's going to be midtime next week. You know that, right? Now, Monday, I need you to be around. I'm actually going to walk you through practice questions the way I did in the midterm one. I'm also going to do it on Monday. Tomorrow, Saturday, I'm actually going to pose midterm 2 practice question without solution. You tried it out, but by Monday, I'm going to post the solution. Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.